Hi everyone, today we will present our project on membership inference attacks and privacy defensive. Many machine learning systems hide their training data and model parameters while exposing only prediction results. But does that really protect privacy? We study whether an attacker can determine if a specific sample can use to during training. To answer this question, we built an evaluation pipeline on CIFA or 10 image classifiers and tested several attack and defensive strategies. Our key finding is that the overfitting significantly increases the privacy linkage, while stronger privacy protections often came with a trade-off in model performance. Let me start with the motivating behind this project. A common assumption is that if we hidden training data on model parameters, user privacy is protected. But in practice, deployed machine learning systems still expose prediction scores, and those outputs can leak information. The answer we can ask is very simple. Can a attacker tell whether a specific sample was used during a training? In our setting, the attacker can only has black box accesses. They can query the model with an image and observe the output probabilities, but they cannot see the model with our training data. The goal is to determine whether the image is a member of the training set or a non-member that the model has never seen before. The key idea is that training samples often receive lower loss and higher confidence than unseen samples, and attackers can exploit those differences. Finally, we evaluate attack success not only by overall accuracy, but also at very low false perceptive risk, since even a small number of high confidence privacy leaks can be harmful. Now let's look at how we actually perform a membership inference attack. The idea is simple. We start with a candidate image and query the target model. The model returns a probability distribution over the 10 CIFA or 10 classes. Instead of using the prediction directly, we extract several features from the output. This includes cross-entry loss, prediction, confidence, entropy, whether the prediction is correct, the full probability vector. We then use these features to estimate membership. We evaluate 4 attacks in total, 3 sample threshold attacks based on loss, confidence, and entropy, and 1 learned logistic regression attack. The intuition behind all of them is the same. Training samples tend to receive lower loss and higher confidence than unseen samples. After computing the membership scores, we choose thresholds on a training split and evaluate attacks on a separate test split. Finally, we report several metrics, including attack accuracy, AUC, and TPR at very low false positive rates.
Now let's look at our experimental setup. We built a single reproducible pipeline on CIFAR10. The dataset was split into 4 disjoint subsets: a target training set, a non-member set for tech evaluation, a validation set, and a held-out utility test set. For the target model, we mainly use a small CNN with 3 convolutional blocks. We also included a CIFAR style ResNet 18 as a sanity check to make sure our observations were not tied to a single architecture. We then evaluated 4 membership inference attacks, 3 threshold-based attacks using loss, confidence, and entropy, and 1 learned logistic regression attack. On the defense side, we compared several common regularization techniques, including weight or weight decay, dropout, label smoothing, and early stopping, as well as DPSGD, which provides formal differential privacy guarantees. Finally, all experiments were run in the same CPU environment. So our goal was to study relative privacy trends rather than archive state-of-the-art classification accuracy. Now let's look at the main defense comparison. The first observation is that the strongest attack across all conditions is actually the simplest one, the loss threshold attack. For the baseline model, the base attack achieves an AUC of 0.539 and a TPR at 1%, FPR of only 1.1%. Since random guessing corresponds to an AUC of 0.5, this indicates that some membership information is leaking, but the leakage is relatively modest. More importantly, all seven conditions fall within a very narrow AUC range from about 0.522 to 0.541. The most prevalent setting is DPSGD, which reduces the attack AUC to 0.524. However, this important comes with a significant utility cost. The model's test accuracy drops to only 34%. So the key takeaway from this slide is that reducing privacy leakage is possible, but it is not free. A lower leakage often comes at the cost of lower model performance. Now let's look at the privacy utility trade-off. The x-axis shows that accuracy, so further to the right means better utility. The y-axis shows attack AUC, so lower means less privacy leakage. Ideally, we'd like a model in the lower right corner, higher accuracy and lower leakage. But if we look at the plot, there isn't really a clear winner. The baseline model and the most of the regularization-based defenses sit in the upper right area. They perform well, but they also leak more information. DPSGD reduces leakage, but it also lowers model accuracy quite a bit. So the main message here is that privacy and utility need to be considered together. If we only focus on reducing leakage, we might end up with a model that is much less useful. That's why we evaluate both dimensions rather than looking at privacy metrics alone.
Now we come to main technical findings of our project. To directly study the relationship between overfitting and privacy leakage, we intentionally trained a heavily overfitted model. We use only 1,000 training example and train a small CNN for 18 epochs. The result is striking. The model reaches 100% training accuracy, meaning it has essentially memorized the training set. However, its test accuracy is only 14.1%, creating a training test gap of nearly 16 percentage points. Once this happens, membership inference becomes dramatically easier. The learned attack reach an AUC of 0.898, and the attacker and the accuracy of the attack is about 18.7%, which is far higher than anything we saw in the defense comparison. And what's even more interesting is the comparison with the other two settings. When we train for only 20 epochs or increase the training set size to 3,000 examples, the attack AUC stays around 0.58, but once the model becomes heavily overfitted, the AUC jumps to almost 0.9. So the key lesson is very clear. As the generalization gap grows, privacy leakage grows as well. In other words, memory creates the output differences that membership influence attack exploit. And before we wrap up, here are three main takeaways from our project. The first is that simple attacks can already be surprisingly effective, and the loss threshold attack consistently performs the best across all of our experiments. And the second is that privacy and accuracy are not the same thing. The strongest leakage appeared in the heavily overfitted model, not necessarily in the model with the lowest accuracy. And the third takeaway is that no FPR metric matter. Looking only at average attack accuracy can hide important privacy risks. There are also some limitations. Since everything was run on CPU, our model are smaller than less optimized than a full-scale C410 benchmark. Our DPSGD evaluation is also limited to a single privacy, budget, and configuration. So we view our result as evidence of overall trend rather than definitive performance numbers. In conclusion, overfitting is the biggest driver of membership leakage in our study. We also saw that strong privacy protection usually comes with lower model performance. So when evaluating privacy, it's important to look beyond accuracy and consider both leakage and utility together. Thank you, and we're happy to answer any questions.